And we're going to do that by learning about what's called vector components. We're going to take vector components using the geometry of the right triangle in order to add vectors like scalars, and then we will have a right triangle again that we can turn back into a final vector. What do I mean? Okay, let's do vector components first, and then we'll come back to this. Let's just say I have an arbitrary vector. I don't care if it's a displacement, velocity, force, whatever. It's an arbitrary vector, so I'm not going to give it units, of length 3 at an angle 20 degrees above the minus y-axis, not the plus y-axis, above the minus y-axis. Okay, so let me go ahead and put that on a coordinate axis. So you always have to put your vectors on a coordinate axis, and when you're analyzing each individual vector, you must put it so it's tailored at the origin. Okay, so this angle here is 20 degrees. So what I want you to recognize is that we can actually break this vector up into two vectors, one that is parallel to the x-axis and one that's parallel to the y-axis. What do I mean? Okay, so let me just break it up into red components. These are what are called components. The x component of the vector is the projection of the vector onto the x-axis. So that means we drop a perpendicular down to the x-axis and we draw the vector that goes to that perpendicular. So that is what's called the x component of the vector. So we call that a sub x. The y component of the vector, we drop a perpendicular to the axis. So this is a perpendicular. And then we draw the vector that goes from the origin. We draw the vector that goes from the origin to where that perpendicular comes, and that is called the y component of the axis of the vector, the y component of the vector. So what do these components mean? Well, the components allow us, we can do this to any vector. So we can break up any vector into vectors that point along x and vectors that point along y. And if we want to add them, we can then add all of the x components because they're all parallel to each other. Then we can add them like scalars. And we can add all the y components because they're parallel to each other, so we can add them like scalars. So this is the way we're going to add vectors. Now, what do these components have to do with that vector? Remember, I just defined a component as dropping a perpendicular to an axis, an arbitrary axis that we have defined, and then drawing the vector to where that perpendicular goes, right? So the point is that if I take a sub y, this vector a sub y, and I just move it over so that the tail of y is at the head of x, what do you think? A sub y, whoops, I didn't draw it perfectly square, I should have, but anyway, that is a sub y just moved over, right? A vector doesn't change when you move it over, I just move it over there. This is a sub y, and notice, what is the relationship between the vector a and a sub x and a sub y? A is the sum of those two vectors. Because the vector A goes from the origin up to here, right? Up to here. And the sum of that is the sum of the two vectors that start at its tail and end at its head. So A is the sum of those two vectors, except for the fact that all I wrote was a sub x and a sub y as their magnitudes. A sub x is actually pointing in the let me be careful here. Hold on. Rather than trying to denote the directions, let me just be more general and just say a sub x is this vector and a sub y is this vector. I had written them as magnitudes, but we can write them as vectors. A sub x and a sub y. So A is simply equal to the sum of its components. A is equal to the sum of its components. And that's always going to be true for any vector. Any arbitrary vector is going to be the sum of its components. Okay, that's important, right? So that we can say, instead of using A, I can just use a sub x and a sub y. Now, in terms of direction, we could have written this as A equals a sub x, which points in the minus x hat direction, plus a sub y, which points in the y hat direction. Okay. So we could have written that instead of writing the vector signs. Okay, so we can find the length of we can find this magnitude a sub x and this magnitude a sub y. How do we find those? We're going to find those using the geometry of the right triangle, right? Geometry of the right triangle. Okay, this is something that you should know. Remember, if we've got a right triangle, what does that mean? It means a shape with three sides that has a right angle in it. That means there's two other angles. We can call this theta 1 and this theta 2. And we know that theta 1 plus theta 2 plus 90 degrees is equal to 180 degrees. First of all, that's one thing we know about triangles, is that the three angles have to add to 180 degrees. A right triangle has a 90-degree angle. So that means if theta 1 is 30 degrees, theta 2 is 60 degrees, right? So on and so forth. If theta 1 is 45 degrees, theta 2 is 45 degrees. Okay. We also know that if we have this, let's just look at the angle theta 1. The opposite side to theta 1, so if we're just looking at theta 1, the opposite side, the side opposite theta 1, right, which is over here, we're going to call that the opposite side, opposite. The side adjacent to theta 1, which I'm going to call, see, that's this one down here. I don't know if you can see those yellow arrows, doesn't matter, because I'm just going to call that side the adjacent side. And then the long side of the triangle, you should know, is called the hypotenuse. Opposite, adjacent, and hypotenuse. And we know the relationship between the angles and the sides. It's that old saying called SOHCAHTOA. We use this all the time in physics. SOHCAHTOA. What does that mean? It means that the sine of an angle, in this case theta 1, is equal to the opposite over the hypotenuse. It means ka, the cosine of the angle, theta 1, is the adjacent over the hypotenuse. Toa, the tangent, toa t, tangent of the angle, OA, is the opposite over the adjacent, right? So here, SOHCAHTOA, S means sine, C means cosine, T means tangent, O means opposite, H means hypotenuse, A means adjacent. So this is how we know the relationship between the angles and the sides. Notice that it depends on which angle we're given. If we're given theta 1, we use these. But if we're given theta 2, everything switches, right? Theta 2, the opposite side is what's now called the adjacent side. So you got to be careful of that. You got to be careful of defining your SOHCAHTOA from the angle that you know. So we could say that actually, because I've already called sine of theta 2 is its opposite. The opposite side in this case is the one that I called adjacent over the hypotenuse, and that's just confusing. But that is true because I called it adjacent. Or I would just rename them. Right, makes more sense to just say, oh wait, that's probably not the best idea. If I'm looking at theta 2, I'm going to call this opposite and this adjacent, and then I can apply SOHCAHTOA, right? Sine of theta 2 is now the new opposite over the hypotenuse, etc. Okay, just be careful about which angle you have and always look at your right triangle. Don't assume. Just look at your right triangle and figure out which is the angle you're interested in, which is the opposite side, which is the adjacent side. We also know one other thing about the right triangle, and that is the Pythagorean Theorem. Which is often written in terms of A, B, and C, but in this case I've got opposite, adjacent, and hypotenuse, and it is that the opposite squared plus the adjacent squared equals the hypotenuse squared. That's the lengths of those sides, right? The lengths of those sides. Oh, I didn't say that. Opposite means the length of the opposite side. Hypotenuse means the length of the hypotenuse. Oopsies. Those are the lengths of the sides. So if instead I call the hypotenuse C, and let's go back to my purple. Forget this theta 2. Let's just go with theta 1. And let's call this adjacent side A and the opposite side B. So let's just clean this up a little bit. Okay. Then we've got A squared plus B squared equals C squared, and the sine of theta 1 equals B opposite over hypotenuse, B over C, etc. Okay, we can write it in terms of A, B, and C instead, and that might be a little clearer. That's the geometry of the right triangle. So we have to use that in order to find the components and do vector addition. So for example, let's say, let's go back to my vector, which was length 3, 20 degrees above the plus y-axis, and let's go ahead and take the components. So from this right triangle, you can see that the sine of 20 degrees is equal to a sub y, the length of the vector a sub y over a, the length of vector a. So just as an aside, a means the length of vector a, or the absolute value, often we call it, but that's the magnitude of vector a. Magnitude, which is always a positive quantity, always a positive quantity, always a positive quantity. I say that over and over again. Okay. And so a sub y is the magnitude of vector a sub y, etc. Okay, so sine 20 degrees is a sub y over a. And so therefore, since a is 3, right, a sub y must equal to 3 sine of 20 degrees. I do not like this color. This color is kind of ugly. Kind of poopy colored. Okay. And then a sub x. We can use cosine, or we can use Pythagorean theorem, right? But we can use the cosine. Cosine of 20 degrees, cool blue, is a sub x over a. So therefore, the magnitude of a sub x is 3 cosine 20. Now, this is just like gonna be a problem for a lot of you. You will often see the way we draw our vectors that the x component is the cosine and the y component is the sine. But that is not necessarily true. This came from the geometry of the right triangle. And you have always, and this is what I was trying to say on the other page, you've always got to look at the angle and look at which side is opposite and which side is adjacent and write this out to make sure that you've got the right component. Because sometimes a sub x is going to be 3 sine 20 and a sub y is going to be 3 cosine 20, depending on which angle, right, which angle you're given. Okay, anyway, we can go ahead and plug this back into the calculator. You can even check your math to see that 1.03 squared plus 2.82 squared indeed equals 3 squared. Check. Or we could have figured out this 2.82 from the Pythagorean theorem instead of from geometry. So what do we know? We know that A is equal to 3 units, 20 degrees north, I'm sorry, not north, 20 degrees above minus y-axis. We also know now that it is equal to 2.82 in the minus x hat direction, because that's pointing to the left, plus 1.03 in the plus y hat direction. So that is the way of writing. So this, we've written our vector in what's called magnitude direction form, magnitude and direction. And this, we've written our component in, our vector in component form. Which one's better? Neither. Unless you're asked for magnitude direction or component form, you can always write your vector in either form. Magnitude and direction form or component form. They're both a complete description of the vector. Just want to make sure you noticed that this vector here, that vector there points in the minus x direction. And when we did the geometry of the right triangle, it just gives us a positive number. We have to recognize that it points in the minus x direction by looking at the picture and explicitly put that sign in for the direction, right? So you're finding the component, the magnitudes of the components, and then you have to look at the direction of the vector. Magnitude of the component, and then you have to look at the direction of the vector. That's how to write it in component form.